Structural mechanics, as all of you know, let me get the screen here. As all of you know, the NCEES, they have exam specifications, and all of you are familiar with it. And the exam specifications are given their website, and the website for the NCEES, I encourage everybody to visit it from time to time to make sure that you are following the news. And I always myself, I do it, but just in case if I missed it, I really appreciate if you can visit the NCEES from time to time. As you know, the NCEES for the Civil Breadth AM, they have 8 chapters, and this is the same chapters I have it in all my 3 books, or my books in general. The project planning, means and methods, soil mechanics, and if you flip the page, you will find that the structural mechanics is the topic after that. So if you go to the NCEES website, or if you open any of my book or other books, they have it also, I believe, you will find that this is what they have 6 questions out of 40 for the AM, which means about 15% for structural mechanics. And these are the topics listed under the NCEES exam specifications. Dead and live loads, trusses, bending, moments and stresses, shear, axial, combined stresses, deflection, beams, columns, slabs, footings, and retaining walls. Those are the topics, and this is exactly what I did in my book. The chapter goes exactly in the same order. This is chapter 4 of my book. It's a very healthy chapter. It does have a lot of discussion, and we already covered that during the class. And today I will do my best to bring the most important topics, but we need to solve problems. The problems that I'm going to send to everybody, those who are attending today, I will be glad to send it to you. As you know, I started with mini exams series during the spring semester. This is the mini exam number 3, for example, which was related to the structural mechanics. So the structural mechanics. So it does have some problems, maybe 1 or 2 problems from another area that we covered before. Normally I overlap, for example, a quantity takeoff method. If you recall, we talked about this, and building with RSS. As you can see, this is one problem. We are not going to cover this today, but the practice exam, sorry, the mini exam number 3, it will be sent to you. Normally, I try to make the mini exam in the neighborhood of 25 problems related to the topic we are talking about: structure analysis, or structure mechanics, soil mechanics, means and methods, hydraulics and hydrology, soil mechanics, foundations, name it. All these topics, the 8 topics. So I'm expecting that all of the 8 topics will be covered in 8 mini exams. So mini exams, I can remember, I believe I stopped after mini exam number 3, I believe. So I will do all my best to go back again to start the mini exams series, mini exam. So today we have mini exam number 3. I will cover as much as I can today from this mini exam, but when you receive it, please solve it, and I will be glad to provide you a handwritten solution. I was working on them because some of you, or most of you, in fact, they asked me during the class. Okay, so I think some of them are typed, some of them are handwritten. I have both. But we need to practice as many as we can. Don't slow down. Whatever your exam day will be, okay. If you have seismic and surveying, also don't slow down. I know the seismic and surveying also, I believe they moved it, or they cancel it for the time being until they clear the issue about the virus, and hopefully that they will resume offering the classes, the CBT exams again. So structural mechanics, which is our topic today. So if you look to the structural mechanics, topic. The NCEES, they have about 7 problems, and we solve all of them during the class here, to the best of my knowledge. We solve all of them. And if you remember, this was the first problem. This is from the blue book. And I don't know if they are going to come up with a new series of books or not this coming July. These books here, the practice exam books. I don't know if they are going to come up with another series or not. I believe I asked them and they said probably they are working on something. But for the time being, let us stick with what we have right now. And this is one problem, for example, about the uplift force. Okay. Another problem, 115, related to trusses. This one problem here, if you have the blue book with you. Number 116, something related to the maximum bending stress, sigma max. Okay, bending slash flexure, we call it flexure or bending, whatever name it they are using. And this is basically the MC over I, this famous formula. Sigma max is equal MC over I, the moment, times C, the distance from the neutral axis up to the extreme fibers, and I is a moment of inertia. So trusses is a topic that we need to be mastering this topic. Let me go back again to the problem that about the uplift forces. Uplift, okay, forces. We need to understand this concept also. Trusses is the second one. Bending stresses, which is this one here, problem number 116, bending stresses or flexural stresses. Bending stresses. As I told you, we call it also flexural stresses. Okay, or flexural stresses, we need to be familiar with that. Also, this is related to the bending moment, because M is a bending moment. So we need to know the bending moment diagrams, bending moment diagrams, because sometimes they can give you a loading and ask you what is the correct bending moment. So bending moment diagrams are another area that we need to be aware of. Or another topic, problem 119 is talking about, let me see here, why did this jump? No, there is a jump here, there is page, probably the pages are, yes, they are not in order, so this way I said what's going on. 117 is another beam, simple supported beam, and here's talking about the maximum shear. So maximum shear. And the word maximum shear here, it could be maximum shear force or maximum shear stress. Okay, and the problem, be careful with the language. Here he said that the same maximum shear in the beam under uniform load. Okay, so the maximum shear force, he's talking about the V, which is a shear diagram. Shear diagram, which is another diagram related to the load diagram, shear diagram, moment diagram. So this is, we use letter V for it, okay? Like the seismic, we use V for the base shear. Here we're using this for shear force. And we need to be aware of the difference between shear force and shear stress. Shear stress, okay, if he gets maximum shear stress under bending, which is this scenario here, because this beam will be like this. Under the concentrated load, we have compression and tension. So this is bending. Under bending, shear stress under bending, we call it tau. And this tau is given by this equation, VQ over IB. This is an equation. I will be glad to go over it and show you the distribution. This is called shear stress under bending, IB. Okay, and we cover this a lot in the FE, or you cover this a lot in the FE. I don't expect for the civil AM to be you having a question like that, but just in case. Normally, I don't assume that anything will be excluded based on the general description of the NCAAS. Always I say shoot for the moon, and if you miss, you are going to land among the stars. So always let us shoot for 150%. Okay. Now the exam, April exam is cancelled, and now we are heading to October exam. October exam. I need you to make to October exam is the last NCAAS national exam you are going to take. Okay, for the PE. Maybe you are shooting for the SCE later on. After that, no problem. But I'm talking about for the PE. Okay, for the PE, and then I'm talking about the NCAAS national exam. Okay. Maybe this virus came as a blessing, or maybe is I don't like to call it a blessing for some people, okay, because there is no any blessing in any disease. But this delay, okay, let me put it that way. This delay that caused by the virus may be a blessing. So anyway, what happen is not our control, or not under our control. Let us prepare ourselves for the October exam very well. Hopefully the exam will be offered in October, on time, October 23rd. And this is will be, so you have time, try to understand the concept, and if you solve all the problems in my 3 books, I believe you will be in very good shape. I cannot claim anything other than that. So those who bought my books and study in their own, they passed. Okay, so what about if you have the books and have the course? I believe you have a very, very better. This is the second book, if you remember, book number 2. I have 3 books for the civil breadth, the practice problems and solutions, more than about 320 problems. I have here civil practice exams and solutions, and the textbook, the one I showed to you, the one we used it. Okay, so I believe if you study and understand the concept from these 3 books, you will be in very good shape. But this will not really prevent me from saying that you are very welcome to get access to any other materials available in the market, study and solve many problems, as long as you stay within the scope of the NCAAS. Don't go and beyond the scope. For example, this equation here, tau is equal VQ over IB. This is equation maybe for those who are taking structure in the afternoon, structure PM, be ready for that, because this is a topic that normally they included in the PM for construction. Okay. So shear stresses under bending, and we have shear stresses under torsion, okay, which is also we use tau, but here tau is equal TR divided by J. This famous equation, T is the torque, R is the radius, not the radius of gyration. This is R, which is D over 2, and J is the polar moment of inertia, which is IX plus IY, which is the sum of the moment of inertia. So this is shear stress under torsion. This is not a torsion, this is a bending. Okay, when we have a beam that it has compression and tension at the same time, we call it bending. Okay, there is another shear stress, but this we call it direct shear stress. Direct. Okay, and we use tau for it. Okay, all this, by the way, shown in a very nice table in my, or a table. I don't like to, if you don't like to call it nice from my point of view, but probably not nice from your point of view. I put it in a table in chapter 4, which is the structural mechanics. Another problem 118 is talking about the flexural rigidity, the EI, the product EI, flexural rigidity. Okay, E is the moment of inertia, and I is, no, sorry, E is the modulus of elasticity, and modulus of elasticity, and I is the moment of inertia. Moment of inertia. Okay, he gave you different shapes, and he's asking you which one of these has the maximum, or the greatest, as we call it, greatest flexural rigidity. Again, an angle, inverted T beam, inverted I shape, or W shape, and the I shape, which is a standard. This is a standard. This is a standard W shape or I beam, as we call it, I/W shape. This is the inverted, okay, or rotated, as some books they call it, rotated. This is inverted T. This is inverted T beam, inverted T beam or T shape, and this is an angle, an angle. And he gave us the dimensions. It is 1/2 an inch thickness by 6-inch steel plate, all of them made of steel. And the moles of elasticity of steel, as you know, is one number, which is 29 million psi. Or some books, they are using 30 million psi. I have no problem with that. Okay, 29 is the standard number for the E for steel, based on the steel manual, or 200 gigapascal, 200 GPa, gigapascal. So all this we need, okay, to be ready for it. And those are the problems that so far we have 1, 2, and 3, and 4. I believe this is, unless I am missing something here, the pages are not in order. Drainage, yeah. So let us be ready for all these problems or all these topics in order to ace this exam this coming October. So when you receive this mini exam number 3, if you have it already, that's good news. You will find there is a problem shown here. It is a truss problem. The truss given, and we have one concentrated load acting at joint D, and the dimensions are given, and he's asking what is the uplift force, and the truss shown is most nearly. The term uplift force, we saw it shortly before when I put this problem, and the uplift force, it is always tension force, tension or tensile or tension force. I will write as much as you can, but you are very welcome to write after me, and I will scan these sheets and send it to you, so you can correct my mistakes if I do have 7 a.m. So the uplift force, it could be for a beam, or for a truss, or for a frame. So when we are talking about here, we are talking about a force. So uplift force could for a beam, or it could exist in a beam situation. It could be for a frame, or it could be for a truss. So for a beam, for example, if you do have an overhang beam like this, sorry, this phone is, okay, I will turn it off shortly. Okay. If you do have an overhang beam like this is called overhang beam, overhang. The name of beams also and frames, overhang beam. Okay, so if this overhang beam A, B, and C, and let's assume that we have some dimensions here to make more sense to us, at least we can. So if this is 24 feet and this is 6 feet, assuming that, or make it 8 feet at least, making more sense a little bit. And there is a concentrated load, P is equal 8 kips here. Okay, do we have an uplift force? The answer is yes. The answer is yes. How much? Okay, so simply if I some moment about support B, you will find there is a force here, which is a reaction, in fact. Okay, so I will call it reaction at A, RA, or YA. Okay, so if you some moment, sigma moment about B equals 0, and assume clockwise is positive, this is up to you. You can assume clockwise or counterclockwise, but let's assume that. If I some moment here, it is 8 times 8, 8 kips, times 8, I change this to 8 feet. Okay, and this is a clockwise, so it is positive. Minus, I assume this reaction to be down. I know by observation, by common sense, okay, by inspection, whatever you'd like to call it, is down. But if you assume it to be up, it will give you a negative sign. So it is reaction at A times 24 equals 0. I solve for the reaction at A. RA is equal 8 times 8 divided by 24. So this is 8 over 3, and this is kips, or 2.67 kips, and this is going down. I ended with a positive sign. What does it mean, positive sign? Mean that my assumption is correct. If I assumed it to be upward, the sign here will be a positive because in the same direction as a clockwise, and you ended with a negative. That means that my assumption is wrong. So this is an uplift force for a beam situation. Obviously, the reaction here at B, which is B sub y, is equal what? Is equal the sum of these two, 8 plus 2.67. Did I calculate this correct, by the way? Sometimes I do mistakes. Catch my mistakes, please. Okay. So this reaction here is, in fact, 10.67 kips up. Equilibrium. This is coming down, and this is coming down. The reaction here at B must be balancing that. And since we're talking about shear moment diagrams, this is called uplift force. So if he give you a beam like this, an overhang beam, and he told you what is the uplift force, here it is. This is the uplift force as far as magnitude. Since we are talking about shear and moment diagrams, here it is. Here is the support, B as in boy, and here is the support A, and here is what we call them datums or reference lines. So this is V, which is the shear. This is the shear diagram. A shear diagram will show the shear forces. M is the moment. Moment diagram will show moments. And we are using, this is M, here it is. It's like Egyptian M, sorry, my M is a little bit, let's make it nice M, here it is. So let me give you 22 seconds from now, because I know you can do it in 22 seconds. Can you draw the shear and bending moment diagram for this overhang beam? Already I calculated the reactions, or we did it together. I have 8 coming down, 10.67, which is a sum of 8 plus 2.67 going up, because don't forget the equilibrium equations. We're still talking about sigma force X equals 0, sigma force Y equals 0, and sigma moment equals 0. Those are still the three equilibrium equations. They don't change. Before coronavirus, there was 3, and after coronavirus, still 3. Okay. Let me give you some time to draw shear moment diagram, and we'll draw it together and see if we are in agreement or disagreement. Starting now. It is 9:39. I will give you only 2 minutes. Okay, time is up. So for shear V, which is a shear force diagram, they agreed on standard sign convention. And this is standard. It's not up to me or up to you. The moment clockwise or counterclockwise, this is up to you. If you assume clockwise positive, you can assume counterclockwise positive, it's up to you. But the shear and moment sign convention, this is standard. Okay, and they agreed on the shear V to be positive if the force going up, down, or if you like to call it clockwise, I have no problem with that. This is a positive shear. Negative shear obviously will be the opposite. And the same story for the bending moment. The bending moment, they agreed that the heavy phase, where we have compression and tension, this is positive M. And the unhappy phase, like that, tension compression, this is negative M. Those are standards, not optional. Those are standards. And this is why when they ask you about where the rebars should go, the reinforcement for any given structure, you have to consider these, specifically the bending moment. We need to know where is the tension side, where is the compression side, where we are going to place the rebars along the tension side, since concrete is very weak in tension, as you know, and very strong in compression, so put the rebars. These are standard, and we apply these standards here. For drawing shear moment diagrams, we are applying them here. In order to make it easy for you, for shear, start from the left, and anything goes up, go up, anything goes down, go down. It will take care of the sign. So here I have 2.67 kibs at A going down, so I will go down a value of 2.67 kibs. And normally we say that the shear diagram, and normally we put the units here, kibs, kib, and this will be kib feet. After that, I need to move from A to B. There is no load between A and B. So there are two equations. I need you to remember them. These two equations are extremely important. And if you remember them, you will be able to draw any shear moment diagram. These equations are dV by dx is equal negative W, and dm by dx is equal V. The slope of the shear will give you the load with a negative sign. The slope of the moment will give you the shear. These two equations are extremely important, and we talked about them, and please try to remember them. So there is no load between here and here. Since there is no load, I need a shear. dV by dx is the slope. I need a line has a zero slope. Here it is. So this is a zero slope. A line between A and B is zero slope. As you know, the slope, which sometimes we call it theta, sometimes we call it dy by dx, or the rise over run. So if you do have our coordinate system, this is x and this is y. All of us, we know that this line has a zero slope, zero, because tangent zero is equal zero. All these lines, they have positive slopes until we come to the y line or the vertical line where the angle is 90, it has no slope. And all these lines here are negative slope. Slope positive, negative, zero, or no slope. This line here, we call it no slope, no slope. Or simply, if you have your calculator and this angle is 90, if you enter 90 and say tangent, it will give you an error, invalid data. So tangent of 90 degrees, but 0 and 10 will give you 0 because the angle here is 0. So in this case, the slope of a zero slope here, and all this positive, the slope start to increase, increase, increase until we go here where the line y has no slope. So the slope also we need to know positive, negative. So this is a line has a zero slope. It's like the x-axis. Okay. Here I will hit the reaction at support B. I will go up 10.67, but already I have 2.67 here. So this will push me up 8 kips. And I will go horizontal also between B and C because there is no load in between until I hit the 8 kips, and the 8 kips will bring me back and I cross the shear diagram. So this is 8 kip, and this is positive and this is negative. And this is the shear diagram. Kips, 8 kips, or already you put kips here. And so remember the slope and so on. Let's come to the bending moment diagram. There are key points. Always look for key points. Key points. The first key point, I know the bending moment at A is equal 0. M at A is equal 0. Why? Why the moment at A is equal 0? Because the moment at any beam can be calculated or at any structure in general, by the way. At any structure, here we have a beam, it can be calculated either from right or left. If you look to support A, what is to the left of A? Nothing. Nothing will produce nothing, and the moment is equal 0 at A. This is a key point. So I know the moment here is equal 0. The other key point is point C, which is a free end here. Also, the moment at any structure can be calculated either from right or from left. What is to the right of C? Nothing. Nothing will produce nothing, so the moment here is equal 0. So I have two key points, moment 0 here and moment 0 here. So the moment at C, M at C is equal 0. So always look for key points. This will help you to construct the bending moment diagram or the shear diagram if we know these key points, where they are located and where or what are the magnitudes. Okay. We said that we do have a standard sign convention, and this is the happy face and this is the unhappy face. If the beam or the member of the structure, because this is applied also to frames, if the member of the structure, in our case is a beam, having this shape, we call it positive bending moment, M, positive. If it is unhappy face, is a negative. Okay. Sometimes the loading and the shape of the beam and the supports of the beam can be a helpful tool for me. For example, this is an overhang beam, as we agreed at the beginning. And this overhang beam, because it has a concentrated load at the free end, it will deflect or deform. How it will deform? In fact, it will deform like this. This is the elastic curve. This is called, and the elastic curve has an equation. Nobody will ask you. We do this in school, elastic curve. Or the diffracted shape of the beam normally is represented by the equation of the elastic curve. So as you can see here, we have tension and compression. That means that I am having a negative bending moment over the entire beam, by the way. Okay, so now I have a bending moment of equal 0 here, a bending moment of equal 0 here. Let me calculate this area, by the way, the area under the shear. 2.67, which is the height, times 24 feet, which is distance. This will give you an area. So it is 2.67, enter, 24 times. This is 22, so 64.08. .67, enter, 24 times, one more time, 64. If you look to this 8, okay, and this distance is 8, you will find this area is also 64. Let me move this a little bit so it will not bother me here. This area is also 64. Rounding here, if you carry this here, 2.66667, 2.6667, enter, and you multiply by 24, you'll get about 64.000008. But since around 2.67, this is why we have here. But theoretically speaking, the negative area and the positive area must be equal. So if you carry this reaction here, more decimal places, 2.667 kibs, and you multiply by 24, you will get exactly 64. But it's not a big deal. I doubt for the sake of the exam, they will consider the rounding as a source for an error to select the answer A or B or C. This is the area under the shear diagram, and they'll tell you why I'm calculating the area. This is the area, and this is the area, which is basically the height times the. So I have the bending moment diagram. Like this. And let me use a straight edge. And this value here is 64 kib feet. And it is negative bending moment below. So when we draw a datum or the reference line, anything above is positive, anything below the datum is negative. So this is a negative bending moment. And the value here is 64. This line here of the bending moment diagram, is it positive slope or negative slope? If you look to this, it has a positive slope. So dm by dx, this equation here, dm by dx is equal v. The slope of this line is positive because the shear is positive. You see that? This line here is what? Is negative because the shear is negative. So equations are very important. The relationship between parameters are very, very important, and we need to understand that. Makes sense. Any question about this? This is started with uplift force, but it dragged us or dragged me or pushed me to talk about all these things. So we need to understand the shear moment diagrams, calculate the reactions are very important. Draw the elastic curve because it could be He will give you a situation, give you a beam, and he will tell you which of the following elastic curve is the correct elastic curve. Elastic curve is also giving the deflected shape of the beam. Deflected shape. Nobody will ask you to write the equation for the elastic curve or develop the equation. Reactions, uplift forces, shear moment diagrams, relationships, sign convention, slopes, all these things are related to what you might see on the exam. We said that the uplift force also could be for a frame, like the problem given in the NCEES. This is a frame. A frame is a structure consists of beams and columns, like this. This is a frame. We have some kind of a girder or a beam. And we have vertical members, we call them columns. And we have some kind of a bracing system. A bracing system, X bracing in this case. And we have some kind of foundation. And the foundation, the footings, for example, here. And this is an elevation of the structure. And he said that we have a dead load here, and we have a live load here, and we have a lateral load here, wind. So this is a kind of a structure or a frame. Here he's not asking you to calculate any uplift force. Here in our simple problem, the overhang beam, we calculated the uplift force. Here he's not asking you, but he's asking you conceptually. Conceptually, okay. What load combination produces the maximum? Again, keywords. Keywords. Always in any question, either the national exam or the seismic or surveying, they put some kind of keywords. We need to pay attention to this, please, because very, very important. I used to write questions many years. Okay. And always we get directions that the keywords are very important to include some keywords in any question. The word maximum, minimum, what is the average, what is reasonable, what do you recommend, all these things. Okay, so we said that uplift force, it is a tensile force, okay, because I am pushing down for this beam and the beam is trying to go up. I need something to hold it down, So for frames and for trusses will be the same thing. The frames like the frame we just saw, here it is, I have a frame, not necessarily to be braced, but we do have some kind of loading system, these beams and columns, and we have some kind of load. This load, he gave you two loads. He gave you a dead load and live load. And he gave you a wind load, lateral load. And he called this is a footing A. And maybe this is a footing B. And he's asking what is the maximum uplift force? Maximum uplift force for the footing. So what load combination? We have something that's called load combinations. or load combinations. Dead plus life plus wind plus earthquake plus temperature plus H. All these things are given in codes. I can show you some examples of load combinations. So we need to know, do we need to have the dead load plus the life load plus the wind, or just only dead load plus wind, or wind only, or what? This called load combinations, and in the codes like International Building Code or California Building Code or the Steel Code, all these codes, they have a series of equations for us. They tell us, okay, what load combinations should be used. Here it is, for example, we have in my book, for example, which something from the IBC code, load combinations. 1.4 dead plus F, dead plus life plus all these load combinations, you already saw it before. And here it is, another set of equations, load combinations. They call it load combinations using the allowable stress design, because we have two systems, ASD and SD/LRFD. Load combinations. Here for this problem in the NCAA's book is asking what load combinations should be applied on this in order to get the maximum uplift force of footing A, this footing here. He said that dead plus life, or dead plus wind, or dead plus life plus wind. The uplift force in general, uplift forces, or make it, why we do have an uplift force, why there are certain structures, like the simple beam or the overhang beam or frame or a truss, they have an uplift force. Uplift force can be generated due to lateral load or loads. And lateral loads, as you know, due to earthquake load, due to wind, or due to the earth pressure, okay, which is the lateral earth pressure, okay, the earth pressure E for earthquake load or seismic or earthquake, wind, or the earth pressure. So any lateral load or lateral loads will generate uplift force. For example, like this. If you have a building or a structure in general, if you have a lateral load, like earthquake load. So this earthquake load is trying to push the building to rotate about this point O. We'll have what's known as overturning moment, OTM. So if this is H, the height, so we have what is known as overturning moment, OTM. And the OTM is equal E times H. This will make the structure that we do have here, this is a tension, and this is compression. The building will be like this. This is the tension side, and this is the compression side. So it could be earthquake, it could be wind, it could be lateral earth pressure. So uplift force will be generated due to a lateral load or lateral loads. Another source for uplift force unsymmetrical loading, unsymmetrical loading, vertical loadings. Like what? Like this beam here. The overhang beam, it has only one load. Is this symmetrical? No. This is unsymmetrical loading. The loading is acting at a point, okay, that will create uplift force. Unsymmetrical loading. Like, for example, like the truss we are talking about. This truss here, the one we have, let me minimize the problem. We have a load here, P. For example, okay, 20 kips. And this is A, B, C, D, E, F, and G. This is unsymmetrical loading. The loading is acting at joint C, but is not symmetrical. Symmetrical means that it will create a mirror image. This is a vertical load. A vertical load. So if we have these dimensions given, 8 feet, 12 feet, maybe this is 6 feet, and the overhang here is 6 feet. Sorry, let me make it exactly here. Okay. So given this frame, this truss here, excuse me. We use a straight edge. This will create an uplift force at the support G. How much is this uplift force? Here it is. You can apply the same thing that we just talked about. This is a force, a reaction, which is G sub Y. If I sum moment about A, sigma moment about A equals 0, clockwise, positive, I will sum moment here. So it is 20 kips times 6, this one here, this is negative, because I put my finger here, some moment, and this reaction here, a plus G sub Y times 6 equals 0. This will give me G sub Y is equal 20 kips. So this is equal 20 kips. And this will make this reaction here upward. 20 plus 20 will give you 40 kips. Those are the reactions for this given truss. This is an uplift force for this given truss. This is uplift force. Because this force is pushing down, it tries to uplift this, take it up, to pull it from its support here. So I need you to remember that the uplift force could be generated due to the existence or the application of a lateral load or lateral loads for more than one, and unsymmetrical vertical loading. The problem he gave me here, it does have both. It does have both. It does have wind load. Wind load is a lateral load. Lateral load means that coming from the side. Lateral load only. without S. Lateral load. I have only one load here. This is a lateral load coming from the side. These are gravity loads. And these gravity loads, as you can see, they are unsymmetrical. If you put a mirror here or try to, there is no similarity between one side with respect to another, unsymmetrical loading. So if you look to this, you may say, oh, we have something is called the concept of superposition. Superposition. I need you to remember that. We covered this in school. Superposition. Superposition means that you are superimposing more than one case. I can look to this frame like this, as like this. By itself, with the wind only. Plus the same frame but with the life, and plus the same frame okay, with the dead. So if you add this to this to this, will give you this. Agree with me? This is called superposition. And this is the footing A, and this is the footing A, and this is the footing A, the one he's referring to. So the lateral load by itself, for sure, it will produce uplift here. We agreed that any lateral load will create uplift. This is unsymmetrical load, the life by itself, it will create uplift here. Pushing down, so we have uplift here, we have uplift here. And the third load, which is the dead load, it's going to create uplift here. So if you add all these together, I'm expecting the answer should be D, to produce a maximum. Are you following me? So we need to understand the concept, because on the exam, you will not find on the exam problems similar to any problems available in the market. It's just a matter of they come up with the new problems every time, okay? But since I understand the concept, it does not make any difference if he give me a frame or a beam or a truss. Talking about the uplift. Is he talking about the maximum, or he can change this word to make it minimum? Minimum uplift force. Obviously, we design for the maximum, but for the sake of the exam, he can change this word instead of maximum, make it minimum. Is the answer going to change? Is the answer going to be different from D? D will give you the maximum. And you can check the answer at the end of the book and let me know, please. If I did a mistake, sometimes I do mistakes. But if the word is changed to minimum, do you think that the answer will be different from D? Yes. If you ask me for what's the minimum uplift force at the footing A, I will say, wait a second. Wind, not necessarily to happening 24/7. Sometimes we have wind, sometimes we don't. Sometimes during the year we have a wind, gust wind, 80 miles per hour or 90 or 100, whatever the value is. Sometimes we have zero. There's no wind at all. So the wind is not 24/7. But when we design for a structure that it has located in a zone or an area based on the map, and we consider the wind, because the wind could happen one day a year, and I need my structure to be safe. We design for the worst condition. Okay, this life load here is a life load over there on the structure 24/7? No, it's a life like me and you. We are occupying a building, and nowadays most of the buildings are empty. Okay, because of this crisis. But the life is not 24/7, not 24/7. At midnight, even without the coronavirus, at the midnight, okay, some businesses, they have nobody there except very, very few. Security maybe, or somebody taking care of the building, but they are not 24/7. But the dead is always there because it's dead. Dead load, a load by definition that has fixed or constant in magnitude and location. Fixed, okay, magnitude and position. Because it's dead, my friend, is not moving. It's dead. So the dead is always over there. But so in this case, if you ask me what is the minimum, I will select my answer C, which is a dead. Because the dead is always there, 24/7. Life not necessarily to be there, wind not necessarily to be there. But again, for the sake of design, we don't design for the minimum because we design for the maximum, because this structure will have life load. This structure will be subjected one day for a wind, so we design for the maximum, and this is why he selected the word maximum. But for the sake of the exam, I needed to be aware of that the answer could change based on the problem statement itself. Make sense? Everybody is awake and everybody is thinking about the exam, October, okay? Don't think about the stock market, what will happen on Monday. The market will go up and down, don't worry, okay? Going back to the frame, not the frame, sorry. The truss problem I draw here. And the trusses, as I told you, it is always there on the exam. And there are many ways that he can ask you a question related to I draw it again a little bit nicer. And one of you has a question, I will answer you in just a minute. The same hypothetical problem I came up with. I just and if you look to this problem here, this will lead us to the second question about trusses. Not to scale, forgive me for that, but try to draw it as okay. Let me insert, let keep it 6 feet, even it looks like an 8 feet. And we do have a single concentrated load acting at this joint here, which I called it 20 kips. But before I proceed, let me grab this question from one of you. And let's see if I have the cursor here. Here it is. And you are very welcome to communicate with me by asking questions or writing. A truss is a dead load always there too. If the life load is not on the footing, Our friend is asking if they remove the live load from this problem. Let's go again to the problem of the uplift force. If the live load is not there, so the maximum it will be dead plus wind. If the problem is given as like this, let me just make sure that I understand your question, because again, sometimes I answer questions and sometimes I ask myself, did I really get the question correct or not? If not, correct me, because I don't like you to. This is a footing here, is another footing here. Okay. So let me just, again, another problem could be included. Okay. This is A, and this is B, and this is C, and this is D, and this is E. Okay. And the loading that acting on this or this, it is dead load here, and the wind here. Okay, what a coincidence, A, B, C, D. Okay. Okay, just change it to make it. Is this what you meant? The truss by itself is a dead load. I know, but there is a concentrated dead load here. Probably they have AC unit here, or they may have a sign here, okay, or whatever it is. So the dead load is a concentrated load at this point here. Yes, the truss itself is a dead load. I have no problem with that, okay? But this is not the question. So in this case, what is the maximum uplift force due to this given load? This is A sub y here. This will be, it is the dead plus wind, which is another answer. If this is what you meant, my friend, dead plus wind, the answer is going to be B in this case. If the life is not there, if there is no life. Make sense? This is what you meant. If not, please, sometimes if I didn't get the question correctly or I didn't understand, you are very welcome to email me. And my email is very simple, okay, info@passpe.com. Everybody wants to pass his PE, info@passpe.com. When I started this business way back 30 years ago, our website is passpe.com, www.passpe.com, passpe. Way back 30 years ago, okay? I think 30 years ago, if I'm not mistaken, or maybe 29, or whatever it is. Way back, there were only 3 vendors. It is Dr. Chalabati, Irvine Institute of Technology, which I worked with him for about 5 or 6 years. Lindbergh, Michael Lindbergh, PPI. I wrote 5 chapters in his books, Serum book, and so way back, and the FE book way back. Right now, we have about more than 40 or 45 vendors in nationwide. Okay, I have no objection to that. Okay, appreciate every additional business to be added. But so a very simple, passpe.com. When I started the business, I said I need a website very easy to remember. Everybody wants to pass his PE, so passpe.com. Okay, so info@passpe.com and our website passpe.com. Okay, just okay. You are very welcome to email me if you would like to clarify a question or clarify something that probably I missed here, or clarify a topic, or select a topic, said that we did not cover this. Can we cover this? Okay, in the next session, I can add extra half an hour or so, and I can cover it. Or when we meet next time, if there's a mistake, you found a typo or a mistake or an error, I did, please correct me, and I will be glad to review it and correct it if I did something. Okay, going back to the trusses. Trusses are very, very important, okay, for the PE exam and even for the SE exam also. This is a statically determined truss. And we have a very famous equation is equal 2J is equal M plus R. J for joints, M for members, and R for reactions. If this equation is satisfied, that means that the structure is statically determined and you can find the forces and the reactions. And if you look to this, you will find that joints, this is 1, 2, 3, 4, 5, 6, 7. So 2 times 7 equals 2. Number of members, start from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Plus the reactions. I have 3 reactions. This support here is a pin support. So it does have G sub Y. I will draw it in the and G sub X and A sub Y. I draw it in the positive sense, and after that we'll see if we draw them in the correct reaction or not, a correct direction or not. So 3, 1, 2, 3. So plus 3. If you look to this, 2 times 7 is 14, and the 11 plus 3 is 14. Bingo. Statically determined. I can find all the forces and reactions. For trusses, like this truss here, they might ask you to find reactions, which I don't expect because normally for beams we ask for reactions. Number 2, they might ask you about zero force members. Or they might ask you a force or the force in a member, in a specific member, a force in a specific member. Those are the most commonly questions that they might ask you about trusses to check the stability, to check this equation, maybe, but I don't expect that. If it is statically determined or statically indeterminate. Zero force members. We will take a few minutes break and come back, and we'll talk about analysis of trusses, and I will tell you what I suggest as a method to analyze trusses. Okay, and we will continue our discussion shortly. So right now it is about 10:26 California time. Let's meet after 10 minutes. Bring a cup of coffee or a cup of tea. So 10:37 we'll meet again. Thank you. Okay, welcome back everybody after this short break. I hope that you enjoyed the break. Trusses, if life load is on footing B, still a count. This is another question. Okay. I will be glad to address all the questions, but okay, our friend is saying that. What about, I will make problems about all these things, for example, here, and if we are going to add the dead load here, sorry, the life load here, our friend is saying that, what will happen if we have another scenario life load? What about that? I can include all these things, all the ideas you have in mind. Okay, I will add it. Okay, so in this case, we are adding another life load here. Okay, our friend said that if we have uh, uh, um, wind and life and dead as shown, what load combination that will produce the maximum uplift force um, on this footing here? Okay, so another question. Trusses, so I can wrap up this and all these questions. I will be glad, even in the form of a problem, I can ask if my assistant can, or some people can help me to draw these things. My staff here, I will be glad to go over all these combinations. So the trusses, as I said, that um, another topic that we need to be aware of, and the moment you see a truss problem on the exam, I don't like you to jump immediately and say, okay, um, um, I need to find the reactions. So trusses, it could be statically determinate, or statically indeterminate. Our discussion here is limited to this, to determinate trusses. Determinate. So this is for the AM, even for the PM, to the best of my knowledge, for structures, you might see some statically indeterminate. The trusses, those are the structures, or those structures that are connected together with the frictionless bands, members, and the smallest truss exists on Earth is a 3-member truss. Okay, 3 members, A, B, C. It must be a triangular form, or they are forming a triangular shape, and they are connected with joints. We're assuming these are frictionless joints, and the 2J equals M plus R will be applicable in this case. If you count the number of joints and the number of members and external reactions, you will find this equation is correct. When you see a truss, I need you to ask yourself two important questions. Two important questions. Number one, do I need to find the external reactions? Do I need to find the external reactions? Number one. Not necessarily every truss problem that you have to find the external reactions in order to find the unknowns or to find the what is asking you about. Question number two, what method or which method of analysis should be selected? Should be selected. If we are able to answer these two questions correctly and quickly and accurately, I believe we are getting very close to the solution. Okay. As you know, the method, which method of analysis should be selected, because as you know, there are three methods: method of sections, and method of joints, And the third method, which is like method of sections, but we list them also, cut and sum method. Cut and sum method. So method of joints, we have only two available equations, sigma force x equals 0 and sigma force y equals 0. Only two equations available. The three available equations for equilibrium, sigma force x, sigma force y, and sigma moment. But the moment equation is not available here because this is concurrent force system. We call it concurrent force system. And a concurrent force system, the moment equation has no value because all of them, they are meeting at a common point. A concurrent force system is a system of forces. They are intersecting at a common point. So only two available. This is why we say never pick a joint. Never pick a joint has more than two unknowns. More than two unknowns. Because you will not be able to solve it. Never pick a joint has more than two unknowns. Method of sections, we have the three equations. Sigma force x equals 0, and sigma force y equals 0, and sigma moment equals 0. The moment equation will show up. And this is same story for cut and the sum method. We have three equations, sigma force x, and sigma force y, and sigma moment also. So when you look to a truss, you have to decide very quick. Do I need to find these external reactions, A sub y, G sub y, G sub x, or not? Maybe they are not required at all. So don't jump and find them. No. If, for example, he is asking, what is the force in this member? The force in the member CD. This force along this member here can be found without really looking to these reactions at all. Do you agree with me? For example, if I would like to find the force in the member CD, okay, how much is that? So let's assume that this is a question. What is the force in the member CD? Okay, for the truss we're talking about FCD. How much? And I'm going to put the problem again on the screen. Here it is, if you didn't get a chance to draw it. What the force here? And indicate tension or compression. Let me give you 1 minute from now. And let us vote. We are a democratic country. We are going to vote this coming November for a new president. And let us, what is the force in this member here, FCD? How much? The magnitude and the direction, either tension or compression, or the type, if you like to call it. Okay, so we have A, B, C, D. I don't know what's the answer. I didn't, as I told you, just I made the problem this morning with you guys. So let us see. We have answers here. I have 24. You have to tell me tension or compression, my friend. 25K. This is one answer. I don't know if it's correct or wrong. Tell me tension or compression. Because on the exam, most likely he will tell you, okay, he will say that, let's assume 25 is one of the 25 kip T, and he might give you 25 kip C. He might do that, assuming that 25 is among the answers, among the, okay. Okay, so any other answers? Okay, let me see if anybody support this answer or got something different. 26.45 tension, 26.45 Gibbs tension. Okay, this is another answer. Let us see, I have another 25 tension. Okay, so far 225 tension and one 26.45 tension. So let's go to the two questions that I addressed, that the two questions that you need to ask yourself when you see a truss problem. Do I need to find the external reactions? The answer is no in our case, because the reactions has nothing to do with this member here for this specific configuration. So the second question, which method of analysis should be selected? And in this case, I have a member here and I have a joint here. I have two members, FCD and FCB. I can use method of joints. Method of joints, I come with a scissor and cut this out. So I decided to go with the method of joints. Because this is appropriate. So I will draw a free body diagram for joint C. A free body diagram for a joint C. Come with a scissor method of, and take all the members and all the forces. Don't forget anything. This is a joint C. So this is where I cut it. And I have a force here, which is P is equal 20 kips. And I have, this is F, this is CD, and this is CB. So I have a joint with two members and one external force. The slope of this member here is 6 to 8. So it is, if you divide by 2, so this is 3, and this is 4, and this is 5. Here it is. Always use this relationship, by the way. This is, sorry, my drawing is not to scale. This is 8 feet, and this is 6 feet. So this is 3, 4, and the hypotenuse will be 5. Always this. And instead of finding the angle theta and all these things, this is the angle theta. So this force is acting down, equilibrium. So the force along the member CD, it must be going this way. This is the FCD. Balance or equilibrium, because 20 kips is 20 kips, yes. So the component in the y direction of this must equilibrium this, or must balance this. Otherwise, the truss will start to move. Have you ever seen a truss moving on the street? No. Unfortunately, we have viruses. Okay, we have this virus, corona is moving around. But have you ever seen a truss moving around? No. Thank God that I will not go on the street and hit a truss. Okay, equilibrium, everything must be in equilibrium. So I will look to this joint, free body diagram. Don't forget anything. When you draw a free body diagram, don't leave anything. Pick all the members and all the forces acting at the joint. In this case, method of joints, we have two equations, as I mentioned. Sigma force X is equal 0, and sigma force Y equals 0. Because this is called a concurrent force system. The force in the member CD and the force in the member CB and the external force P or external load, all of them are meeting at a common point. So there is no sense using the moment equation. So in this case, I have to select the proper equation. Again, when you have two equations or three equations, selecting the equation is very, very important. Sigma force X equals 0, sigma force Y equals 0. I have to be selective because I need to save time. Sigma force Y is the best one because I have only one unknown. So if you say sigma force Y is equal 0, and I say that anything goes up to be positive, so I have negative 20 kips because going down, plus I assume this force to be a tension. Tension means that the force is pulling the joint. This is the joint C, and this is the joint D. So if the force is pulling the joint like that, we call it tension. If the arrows going into the joint, or the joints, sorry, in this case, we'll call it compression. Agreement with respect to joints. Also, we have another definition, it's called with respect to members, but they would give you the same answer. Stick with one definition and that's it. So, if the, let me pick this here, someone of you is asking something or he give me an answer. Okay, thank you. So right now, the force of the member CD, it's going up, so it is positive because the component is going to be up, divided by the hypotenuse, which is 5, and I will multiply it by 4. Because I need the vertical component. This is equal 0. And I solve for FCD here is equal to 20 times 5 divided by 4. This and this is equal 5 is equal 25 kips. And it came positive. What does it mean positive? That means my assumption is correct. If I assumed it to be compression, the ore is going down, this will be minus. Minus equals 0, you'll find it minus. Sometimes we don't know the direction of the force or the sign of the force. In this case, you can assume it. If you ended with a positive, like this, mean that your assumption is correct. Your assumption is correct. If you ended with the negative, and sometimes we do that, that means my assumption is not correct and I will reverse the sign. Make sense? So I need you to be aware of that. So you can move it from one. But if he asks me to find the force in this member here, this here first, FGF. FGF. FGF, this member here, in this case, the reaction will help me. That means that I can find the reaction first, G sub Y, by summing moment here, and the force along this member is equal to the force that I'm going to get from the reaction here. So I needed to be aware of these two questions, and when you receive my notes, go over them and again. Okay. Next question is the zero force members. Zero force members. Or a zero force member. Textbooks, they have two important rules. Structure textbooks, I mean structure textbook, the one we use it in schools. For undergraduate or a graduate. Some, they came up with another rule, which is, I have no problem with that. It is a repetition or a redundant. Even some came up with another fourth rule. But the two rules that they are the source of all this. Rule number 1, it says the following. To determine the zero force member. If you have two members, two collinear members forming a joint. And there is no load or support at this joint, the two members must be zero force members. Two members are zero force members. This is the rule number one. Non-collinear members. And I will come to rule number two after I explain rule number one. If you have a member AB, a member AB, and another member BC, they are along the same line of action, or this angle is 180 degrees, or the same bearing, we call them collinear members. This is collinear members. Collinear members. They have the same bearing, the same line of action, and we call them collinear members. But if you do have a member AB, and a slight angle like this, whatever the angle is, BC, these are non-collinear members. Non-collinear members. Non-collinear members. They don't have the same bearing or the same line of action. So rule number one is telling me that two non-collinear members forming a joint, and there is no load or support at this joint, the two members must be zero. For example, like this. The same truss we just talked about. A, B, C, D, E, F, G, the same truss. But in this case, I'm not going to put the load here as it was before. I'm going to put series of loads here. B1 is equal 10 kips. B2 is equal 14 kips. In this case, if I come to this joint here, two members, CD and CB, are forming a joint, and there is no load and support. They are far away from support. So blindly, these two members are zero force members, 0 and 0. This is what is meant. So two members forming a joint where the two members are non-collinear. and there is no load or support here, these two members automatically will go to zero, because if you take this joint out as we did and analyze this joint outside, this is joint C, and this is D, and this is B. There is no load here. If you apply sigma force X equals 0 and sigma force Y equals 0, you will come to this conclusion so easy. Make sense? This is a rule number 1. Easy one. Rule number 2 is talking about 3 members. So 3 members forming a joint. Forming a joint in which 2 of them are collinear and there is no load or support at the joint. The third member in that joint is zero force member. This is rule number 2. A little bit is not easy as the first one, rule number 1, but I'm going to translate into English. Rule number 2, obviously this is my Egyptian English. It could be written in my book a little bit differently or in your textbook. For example, in my book, here they are in the chapter we are talking about on page 227. Page 227, if 3 members form a truss joint in which 2 of the members are collinear, the third member is a zero force member provided no external force or support reaction is applied to that joint. Probably they reverse. This is another language. This is an Egyptian English. Here it is. 3 members forming a joint in which 2 of them are collinear and there is no load or support at the joint. The third member will be 0. Let's translate this into English. Okay. If you have a truss like this, A, B, C, D, and E, and assume that these distances are given. And I have a load here. B is equal 24 kips. And I have a load here. B2 is equal 16 kips. So they are saying that rule number 2, we're talking about, it must be 3 members. 3 members. There are 3 members here at this joint. Joint D, there are 3 members. 2 of them are collinear. DC and DE are collinear, the same slope, or the same bearing, or the same line of action, in which two of them are collinear, and there is no support here, and there is no load here. They are telling us this member here is a zero force member. Because if you take this joint out and analyze it in the x direction, this member FDC and FDE, they have components along the x direction, and they must be equal for equilibrium. Again, this is equilibrium. So this is a zero force member. Any dispute about that? Or any disagreement about that? Because you will find that the force along this member, FDC and FDE, they must be equal, by the way. So the components under x direction must be equal. And the component the y direction must be equal. They cancel each other. So in this case, there is no force along the member BD. FBD is equal 0. And please analyze the entire truss and let me know if you find something different from what I just said. So here we have two members forming a joint. Two of them are non-collinear, but I have a load here. So this member exists, the FBC and the FBD, DC, they are exist. This member here and this member here, they have forces. So if for the sake of the exam, they asking what is the force in the member EB, which is this member here. So if you are giving the problem from scratch, without talking about anything, okay, or without explaining anything I just said, let me draw it one more time. Hopefully I can draw it very quick. So this is A, and this is B as in boy, C, D, and E. Also, this is 10 feet, and this is 5 feet, and this is 10 feet. I didn't draw it to scale, I'm sorry. Okay. And I have the two forces here. One is here. And there is one here. And is asking, this is a given truss, assuming that it's drawn, and they may say not to scale, at least don't mislead you, scale, but this should be a little bit bigger. And he's asking you on the exam, find the force in the member EB. This is an internal member here, FEB. So we need to find the easiest way and the quickest way to find the force in the member, EB or BE. So if I remember this relationship between these three members, based on rule number 2, I will say, okay, this is 0. So if I come and take this joint here outside, I can sum force in the y direction and find it directly without really going through many. Because if you use method of joints, you are going to move from this joint to this joint to move here. But if I know this rule, I can do it quickly by knowing that this member is 0 based on rule number 2. 3 members forming a joint, 2 of which are collinear. The third member is 0 as long as there is no support or there is no load here at this joint. So I know the slope here of this one here, which is my scale, sorry, it is 2 to 1, because this is 5 and this is 10. So this is the square root of 5. And I will leave this to you when we meet next time. To find what is the force in this member here. And again, always indicate tension or compression. Always. And the rule, as I told you, that with respect, this rule here, or this sign convention I'm here, this is with respect to joints. With respect to joints. There is another definition for tension and compression with respect to members. They are the same. I prefer the joints, but the conclusion will be the same. If the arrows are pulling the joints, we call it tension. If the arrows pushing the joints, we call it compression. Simple like that. Pulling and pushing. If you like to use the other definition with respect to members, I have no problem with that. I can explain it. But stick with one rule and try to. So going back to our truss, do you remember this truss way back? The one we talked about it? And this is okay, a question. Obviously, we got some answers here. We found that the answer is 25 Gibbs tension. This was the correct answer for this one, as we explain it here. Here it is. So in this case, I need to put a letter T next to it. 25 Gibbs tension. Because I assume it to be tension, I ended with a positive. That your assumption is correct, i.e. tension member. Makes sense. Okay. So going back again to this truss and ask ourselves, based on the two rules, about the zero force members, how many zero force members here for this truss? Answer A, none. Answer B, 1. Answer C, 2. Answer D, 4. Answer E, I will keep answer 5. I added extra answer here. In fact, the FE exam right now, they have multiple choice, and they have A, B, C, D, E. And also for the PE in 2023, as you know, they are going to switch to the CBT. So they might go back again to A, B, C, D, E, F, or something like that. Let's assume that. So how many zero force members in this truss? Either answer A or B or C or D or E. None. 1, 2, 3. 1, 2. Oh, I jumped 3. Okay, that's fine. Okay, 1, 2. Okay. Let's put 3 also, just 3, 4. To give all the option A, B, C, D, F, 5. So 1, 2, 3, 4, 5. Okay, to make everybody happy, at least. So you said that we have all the options. Okay. Shall I leave this as a homework for you, like the other load here, when the dead load is acting adjoint C? But let's pick some answer from you. Maybe it will help. The answer A is none. Okay, I have a friend of mine, he said that none. Oh my God. So all these answers, they have no meaning. Okay. Look at again. Remember, this force is vertical. So this is a hinge support. What is the value of G sub X? G sub X is equal zip 0. If G of X is equal 0, and I pick this joint G as a free body diagram, if this is 0, what is the force in the member AG? If this reaction here, the horizontal reaction is 0, because we have only two. One vertical here, and one vertical here, and one vertical here. And all of them must be equilibrium. Do you remember the uplift force? Obviously, this will be down, but but for G sub X, some forces X will give Gx equals 0. If this is 0, what is this force member here, by the way? Can I say that this is equal 0 also? Some forces in the X, I will take this joint as a free body diagram, and there's some force in the X direction. Agree or disagree? Make sense? Okay, so I will stop here, okay? So just to clarify this, one of you is saying that there are 5. There are 5. Okay, so he get answer F. 5. If this is 0, this is the starting point. I need you to continue, please, and tell me either the answer A or B or C. 1, 2, none. 1, 2, 3, 4, 5. I give you all the options. What about that? So we can move to another topic, and we will, when you receive my handwriting, please look at it and let me know. Okay. So trusses are important, and we need to pay attention. And I hope that what I just talked about this morning is a reminder or a refresher to you. And the more you solve, the more you will be able to analyze. So there is no limit. Always, I say, the sky is the limit. Always look to the in the mini exam, the one I will send it to you today, or maybe somebody will send it to you Monday. It depends on my time. If I'm able to send it today, for sure I will do, because I do have another class today at 4:30 today, 4:30 to 7:30. This is the last free surveying class. It is a free surveying class in this quarter. As you know, surveying and seismic, they are surveying class. This is BM also. It is Pacific Standard Time, California time. So if you'd like to join me, you are very welcome. I believe the ID is available on our website, but the ID for this one, the ID, again, you will go to www.joinwebinar.com. The ID is 252 359 611. Today is the last one tonight. Tonight or tomorrow? Let me know. Tomorrow I have seismic, I believe. Forgive me. No, it is tonight. That's correct. I look to my. So you need just www.joinwebinar.com as webinar.com as you join me today, and they enter this ID, you will be able to join me. This is for surveying only, okay? For the special California surveying exam, as all of you know. So it depends really. And tomorrow also I'm busy with transportation and I have seismic. So if I have time, for sure I will be sending my notes and sending you the mini exam number 3. And I will do all my best to come up with the 8 mini exams. 8 mini exams. So 8 mini exams. I will do all my best, even I'm extremely busy, but pray for me to stay healthy, and I pray for you to stay healthy. Okay. So Go over them and solve all of them. Take it seriously. Some of them, okay, are lengthy. Some of them are not lengthy. And be selective. Be selective, okay? Try to uh, um, um, trusses. I have a lot of truss problems here, by the way, a lot. Three cable structures, okay, or the um, three cable system. It might be very common. You might see something like that. Apply equilibrium equations and the free body diagrams. Some problems related to a little bit of materials. I included also here related to the stress strain curve for steel, which we'll talk about it here, and we'll talk about it also in material section, chapter 7 of my textbook. And they're asking what is the modulus of resilience? Modulus of resilience. Okay, we need to be aware of that. Very quick, just a reminder. So, and when you solve it, take it seriously. If there are 25 problems, so 25 over 40 times 4 hours. So theoretically speaking, by proportion, okay, uh, uh, um, you can say that uh, uh, the percentage, probably some of you already calculated that, 25 over 40, which is times 4 hours. So this is supposed to be 2.5 hours. Okay. So when you receive it, just close the door and spend 2.5 hours and have your reference next to you and see if you can finish it in 2.5 hours or not, assuming that the same proportion. And they try to challenge yourself. Don't look to the solution. Even if you have a solution from another source, or try to solve it, always solve these problems as if you never saw them before. Don't say, oh, I know that, I know that, I know that. No, don't say that, please. And that's why I decided to have these summer workshops, because I'm afraid that you will say, I know that, and you will come as closer to the exam. And this is why the passing rate for repeat is 50% of the passing rate of the first time taker. This is NCEES statistics. It's not, they are not my statistics. Just assume that you know nothing. Assume that this is the first time that you see it. If you know it, that's fine. Solve it again to strengthen your knowledge. To squeeze it in your brain. When you go to the exam, you have no time to, sometimes you have no time to open any book or to look to any reference or to look to any equation. If you are prepared yourself very well, you will be able to ace this exam without any problem. Make sense? Okay. So we have E, we call it modulus of elasticity. Modulus of elasticity. E, which is sigma over epsilon, which is Hooke's law under uniaxial. This is called Hooke's law. Under uniaxial load. Uniaxial. Uni means one. Or some books we write it delta sigma over delta epsilon. A change in stress over a change of strain, which is basically the linear portion of the stress strain curve. The slope of this line is, so this epsilon, which is delta L over L, which is the engineering definition, engineering strain, and this is sigma, which is B over A. So we do have a linear portion, and let me move this a little bit. I should stop, but delta L over L. So the slope of this line is called E, which is a rise over run, which is sigma over epsilon. This is called modulus of elasticity, and the modulus of elasticity E, as you know, for steel, as I mentioned today, is 29 million psi. Modulus of elasticity for concrete, for example, it is a range between about maybe 3 to 7 million psi. Wood, for example, E wood is very small number. This is E wood parallel to green, by the way, because wood, okay, about 1 to 2 million psi. Concrete, we have a very wide range. This is one number. We have another modulus, but not modulus of elasticity. We call it modulus of resilience, or simply resilience. Some books, they call it modulus of resilience or resilience only. This is what? This is the area under the linear portion of stress of sigma epsilon curve. So if you come to the linear portion and take the area under this, the linear portion, this is called modulus of resilience, or the elastic energy, or elastic strain energy, as we call it in seismic design. This area here is, which we sometimes we write it this way, that the modulus of resilience is equal 1/2 epsilon times sigma, but this epsilon must be here, epsilon sub y and sigma sub y. Area of a triangle, 1/2 base times height. And since I know epsilon is equal sigma over E, so I can say this is 1/2, okay, sigma y square over E. This is another equation, by the way, because I know epsilon sub y, okay, is equal sigma sub y over E from this relationship. And I believe I included one problem here, if I'm not mistaken, in mini exam number 3, maybe. Oh yeah, the modulus of resilience, the one I was talking about. That's correct. Here it is. Modulus of resilience. Here it is. Modulus of resilience. So this is the stress strain curve, and this is the rupture or failure here. So basically, all what you need to do, you need to come and calculate the area under the linear portion of the stress strain curve, and this is what they call it, the elastic energy or elastic strain energy. This one here, it does have a name. It's called elastic, or modulus of resilience. We'll call it elastic energy. Energy, or the energy under the linear portion, or the energy during the elastic stage. Or sometimes we call it elastic strain energy. I know the naming is elastic strain energy. Elastic strain energy. So this is modulus of elasticity. This is modulus of resilience. There is another modulus I needed to be aware of, which is also included in the modulus of toughness. Of toughness. Or sometimes we call this is the total energy. Total energy. Total energy up to failure. If there is no failure, we cannot determine the toughness. Total energy, which is basically, I believe I repeated the same problem, This is problem number 23 when you receive it. It's number 23. Problem number 19, modulus of toughness. Here it is, modulus of toughness. It is the area, this is the rupture or failure. So the area under the entire stress strain curve up to, so I need all the area. So it is the entire area. So if you have the stress strain curve like this, and not necessarily to be nice and straight line, they can give you something like this. In this case, we need to approximate. He can give you a true stress strain curve like this. This is sigma is equal B over A, and this epsilon is equal delta L over L, and this is a rupture or failure. R-U-P-T-U-R-E, rupture, here it is, or failure. He will give you some numbers. So the entire area under the stress strain curve up to failure, which we call it total energy. Total energy. And this is very important in seismic design, total energy, which is the entire area under the stress strain curve up to failure. How much energy can be absorbed by the structure is very, very important, because the amount of energy is indication how much damage that will happen to the structure during an earthquake. Always I make an analogy. If there is Mr. Mansour, okay, and somebody came and hit me from the side by, he gave me, okay, hit me, okay, by his hand, give me a box or whatever you call it, okay. If I'm able to absorb the energy that released from his head and I keep standing, that's good. That means that I'm capable of absorbing the energy. But if I'm not strong enough and somebody hit me from the side and I collapsed, failed, okay, I am not able to absorb the energy from his head. So when we have a structure like that, whatever the structure is, and the structure start to shake back and forth under the effect of the earthquake, if this structure, because of materials and because of the way this is constructed and the way it's braced, is capable to absorb energy, it will absorb the energy with minimum failure. Because all our intent from seismic is to save lives, not to maintain, okay, the structure. I need the structure may deform a little bit. It will have a little bit. If I have a bridge, I don't like the bridge to collapse completely and will fall down into the river or whatever the valley. No, if the bridge will suffer minor damage, some cracks here and there, I have no problem with that, and the code will accept that. But I don't like to have a structure failure, that the building will collapse completely like Mr. Mansour here. Somebody hit it from the side with a big hit because he is not able to absorb. So this energy is very, very important, which is called toughness, total energy. Very, very important. And the units, by the way, since it is an area, this is in PSI, and this is inch per inch. Strain is inch per inch. Its dimension is quantity, but we use inch per inch or millimeter per millimeter. If you take the area, you will find it is bound per inch square, which is PSI, and you multiply inch per inch. So normally we use bound inch per inch cubed per volume. And you will find that the units like this, here it is, kib inch per inch cubed. So this is something I needed to be aware of. Okay. Stability, we cover it twice. I covered the stability in structure analysis. Also cover stability in geotechnical when we are talking about retaining walls. But if you look to this crane subjected to some kind of loads or loadings, different loads, and we have a load here, and a load here, and a load here, and a wind load here, and another wind load here. And he said that the factor of safety was given to you as 1.5, overturning. And what is the maximum load that can be carried by this truss, by this crane, sorry, without tipping over this point? Oh, because if this load is too big, this is going to tip over the overturning moment. So he said that the factor of safety again is overturning. Okay, we need to know that because it could be in the AM, it could be in the BM. For construction group, they might see something like that. So we cover also the factor of safety against overturning and against sliding. So the factor of safety, it is the ratio between two things. Something try to resist and something try to disturb. So the resisting either forces or moments over the disturbing forces or moments. Or moments. And this factor of safety must be greater than 1. We use, or the IBC code right now is asking for 1.5 as a minimum factor of safety under a static load, 1.5. So the factor of safety must be greater than or equal 1.5 for overturning and the sliding. And the factor of safety against overturning. It must be greater than or equal 1.5. So we need to be aware of that. The factor of safety, how to calculate it. And this is a very good problem. Don't forget a force or don't forget or use the arm, the moment arm, the wrong moment arm. This is a very common problem that go over, neglect the tower sway. This is, okay, the assumption here. What is a maximum? You see the word maximum, big load. Please go over it and let me know. I believe equilibrium, very important. Deflections also. Shear moment diagrams for beams. Already we talked about that. Deflection. Columns are very important also. I did not include problems about columns here, but I could include it in the future. It is a very good reminder for me. Columns. They might ask you about columns. Buckling of columns. And let's conclude this. Columns are vertical members carrying axial load. And the first column that was studied by the scientist, Professor Euler, he is a Swiss mathematician. He used a vertical column. It has a pin or a hinge. And he calculated the maximum load, P, to cause the column to be buckling or to buckle like this. And he called this is a critical load, B critical. And you'll find in my book and other books, there are two equations. B critical is equal pi square EI divided by KL square. This is the general equation. This is the general equation for buckling. Where K is called effective length factor. Effective length factor. And this is, for example, K is equal 1 for a column like this, that it has hinge or bin, HH. K is equal 0.5 if both ends are completely fixed, it's called FF, and is equal 0.7 if one end is fixed and the other end is hinge. So this is HF. Those are the most common cases, and I have a table in my book, and this table is taken from the steel manual. The steel manual. So this is equation. Okay, L is the unsupported length, E is the moment, the I is the moment of inertia, E is the modulus of elasticity. We need to be aware of that. The second equation, which is the critical stress, sigma critical, which is basically the B critical over the area, because sigma is equal B over A. So in this case, we can simplify this equation as pi square E divided by KL over R square. This is the second equation, also you'll find it. And this is the general equation, KL over R. Again, R here is not the radius, no. It's called, R is called radius of gyration. Radius of gyration, which is the square root of I over A. So R is not the radius of the shaft, no, it's called radius of gyration. Radius of gyration. Radius of gyration. Radius of gyration. K is still the same and L is still the same. L is unsupported length. So these two equations are very important, and you might be asked about these equations, okay, either to calculate the critical load or the critical stress, or it could be a conceptual question like this. Okay. Okay, 4 columns. Column A is fixed at both ends. Column B is fixed hinge, hinge, or bin, HH. And this is HF. And this is fixed, and this is fixed, and this is the free end, like the flagpole, for example. 4 columns, as shown, made from the same material and the same cross section. So same material. So the modulus of elasticity is still the same material, i.e. E is the same for all. And same cross section. Each word has a meaning, i.e. I is the same, and same length, i.e. L is the same for all of them. And the question is, which column, so LUMN, which column, only one A column, only singular. Okay, let me take this out. Will have the largest buckling load. Which column will have the largest buckling load? That it will carry the maximum buckling load. Buckling is one of the failure mode, as you know. We talked about that. Buckling. This is called buckling, which is one of the failure modes. We have modes of failure, as we call it, modes of failure, as you remember from quantum mechanics. If you take quantum mechanics or strength of materials, advanced modes of failure is slip or flow, slip or flow. Number two, pulling apart or separation, pulling apart or separation. And finally, number three, buckling. So buckling is one of the modes, okay, of failure. So we need to prevent this for bridges and for columns in buildings and so on. So which column will have the largest buckling load? And they can give you the answer A. He will give you column B, for example, answer B. Column C, answer C. Column C or column D, sorry. And answer D will give you column A. Okay. So I have four columns. Conceptual questions. Which one has the maximum or the largest buckling load that will carry load? Okay. Carry the maximum load before it buckles. From the equation of the buckling load of Professor Euler's, this is called Euler's buckling formula by the Professor Euler. Euler's buckling load, or Euler's buckling formula as we call it. Euler's buckling formula or Euler's buckling load, be critical. Euler's buckling load. As you can see, B critical is inversely proportional to K square. This square. So B critical is equal to, is inversely proportional 1 over K square. I need you to remember that. Where K is called the effective length factor. I know we are using K in transportation, which is L over R, and the R is different R from the R we use today. K, we use it in hydraulics, by the way, when we calculate the minor losses for orifices and for openings and for valves and all these things, if you remember. And the reason I mentioned that because another problem could be, let me finish this first, and after that, it could be like this. Okay, you have two identical columns made from the same material, but they have two different end conditions as indicated. This is column A and this is column B. The same L, E, I, same. And they will say that the ratio of the critical column of the critical load of column A with respect to column B is most nearly, and he will give you four answers: A, B, C, D. The ratio is 1.5, 0.25, or 0.15. Let me show you the four answers. Here it is. The ratio of the critical load of the column A with respect to column B, it is 1, that means they are equal, or 0.5, or 0.25, or 0.15. This is another conceptual question, okay? Not necessarily to be calculations, because we need to be ready for both. Calculation-wise, exams are not only just calculations. No, calculations, yes, they are important, and we need to know how to use our calculators. Calculations versus conceptual questions. We need to be ready for both, please, because so as far as the question number 1 here, and this is number 2 related to buckling. Let us vote. We are a democratic country. As I said, this coming November, we are going to vote again for a president. So we have 4 columns that are identical as for I and E and L. This is same. Which column has the largest buckling load? Column A or B or C or D? Let us vote before we go, or before we end this session. Okay. Okay. Column, okay. So I got some answers. Okay. Now let's go to the second question, which is this one here. Two identical columns have L and E and I are the same, but this is HH or hinge, and this is fixed. The ratio of the critical load of column A with respect to column B, the ratio is 1 or 0.5 or 0.25 or 0.15. Let's get some answers. Okay. I got some answers. What about the rest? We need to vote. Well, voting is very important. Okay. Going back to the question number 1. As we know, the K here, there are something called theoretical K and design K. But for the sake of the exam, we are dealing with K theoretical, by the way, theoretical. Okay, the design K is a little bit higher than the theoretical K if one end or both ends are fixed. But I know that he will ask you that. K here is equal 0.5. K here is equal 1, theoretical. K here is equal 0.7. K here, one of you asked me what this K is equal 2.0. And all this written in my book. You will see it in chapter 4. So again, the critical load, B critical, is equal pi square EI divided by KL square. So the smaller the K, because the K in the denominator, and you square it, the larger the P. So column A will carry the largest load because it has the smallest K. I need you to know that. So the answer is column A, or the answer is D, as in doctor. Okay. Column A is the column which has a buckling load is the largest, which is a column A, which is this one here, because have the smallest value of K. The smaller the K, the larger, because they are inverse proportion, as you can see from this equation. And the inverse proportion to the square of the K, by the way. If you look to this here, this column here, if this is P critical, B critical, the critical load for this one is 4 B critical. This column will carry 4 times the load of this when it buckles. Again, the value of K. K here is 1, and K here is 0.5. But since we square it, it is 1 over 0.5 square, which is 1 over 0.25, which will give you 4. Don't forget the square. Not this why I put half here to confuse you. It is a quarter. This will carry quarter of this, or this will carry 4 times of this. If you call this a critical load B critical, this is 4B critical. Make sense? I need you to look to all these things, and when you receive my notes and you receive the mini exam number 3, go over it, and I will be glad to address any question or any topic that I did not address it today. I will do my best to look to my emails, but bear with me because I have tons of things to do, but I will do all my best to keep you busy this summer. I decided to do that to keep helping you all the way until we join again in the regular classes. So do your best as long as you stay healthy, and as long as you pray for me to stay healthy. We will keep working together until we achieve our ultimate goal is to go and take the exam, and no more exams. National exam is coming October. I hope that it will be held on time, and move on and take your PE, and after that you can relax, unless if you like to, you are shooting for the SE or for any other registration. Thank you very much for coming today. Please let me know. Feedback is very important. Let me know if there is any way I can improve it. I will. I've been doing this for 30 years, and I always listen in order to include any improvement that may be added, and always continuous improvement is the best way to improve our life. Okay, thank you very much. Be safe. Try to do your best to take care of yourself, take care of your family, take care of your neighbors, take care of the entire country. Anything you can do to help spreading this virus, please do it. Physically, mechanically, spraying some kind of material that will prevent this virus from moving around us. Please do that. Okay, any method or any way you can helping the entire world, or you may discover a cure for it, or may discover a vaccine for it. Okay, please do your best. Okay, again, thank you very much for coming. Tomorrow I will be here for the for what? For the I believe this one here. Yeah. Tomorrow I will be here for the tomorrow is 29. That's correct. 29. I will be here for transportation, and I will talk about what we are going to cover in these 7 sessions. Okay, using my transportation books, and you are very welcome to join if you are interested in transportation. If you are not, if you have construction, come on your day. You are very welcome to join, but I will limit myself to the topics related to whatever we're going to cover tomorrow. I do have some agenda in my head, but I call it workshop number 1, number 2, and so on. Okay, so enjoy the rest of your day. If you'd like to join me this afternoon for the surveying class, 4:30 to 7:30, I will be limited also to the surveying questions related to the special surveying exam of California. I know they canceled the exam, unfortunately they canceled it, but what can we do? We will do our best. So from 4:30 to 7:30 p.m. tonight, and tomorrow I have also the same, but for seismic. Okay, so but a different ID, by the way. Seismic is not the same ID. Okay, call me if you would like to join me, and tomorrow is the last day also for the seismic. Or let me write it down if you'd like to join me for the seismic. I have no problem with that. Seismic also tomorrow, which is 329, and this is the seismic. I will cover chapter 15 and chapter 16 of my textbook, from 4:30 to 7:30 also, Pacific Standard Time. And the ID for that, let me see here, seismic. Here it is. ID is 882-371-739. 739. Those are the two, and they will be void after tomorrow. So this will be void tonight after we finish this. That's no more, and this will be also after tomorrow will be no more. So this, but for the free, still the same ID is going to stay with us all the way to the this ID here. Excuse me. This ID here will stay. Okay, it's only one ID for all these classes. For all these classes, one ID. Thank you very much. Okay, I wish you the best. Bye-bye. Yeah, I know that. I know. Okay. Thank you very much. Sorry that they canceled the exam, my friend, but what can we do? Okay. So let us do our best. This will give you more time to prepare. So let's prepare it, and good night, everybody, or good afternoon.